Hey guys, so this is section 9.2, the chemical potential of a component in the gas and solution phases. So start out with what we know. We know one thing, and that is that for every component I in a solution, the chemical potential of that component in solution is equal to the chemical potential of that component in the vapor phase at equilibrium. Now back in section 6.3, we derived the chemical potential of a species in the gas phase related to its partial pressure by this equation right here. We said that the chemical potential of that species in the vapor phase is equal to the chemical potential of that species in standard states plus RT ln, the partial pressure of that species over the 1 bar, basically, standard pressure. But because the chemical potential of that component, of every component in the vapor phase, is equal to the chemical potential of that component in solution, we could write this equation for the solution phase too, just as well. So we'll just call that mu sub I, the chemical potential, and it will apply to both the vapor and the solution phase. That means now we can write this. Mu sub I, the chemical potential of component I, is equal to the chemical potential of component I in standard states plus RT ln of the partial pressure of that component over the standard pressure, which is 1 bar. So remember this because we're going to use it in just 1 second on the next slide. Now for pure liquid. Okay, that was a solution. For a pure liquid, we know that also the chemical potential of that liquid, the asterisk here, remember, means pure substance, is equal to the chemical potential of that species in the vapor phase, and we'll just call that mu star, sub I. And that means we can write the same sort of equation for the pure solvent. Mu sub I star equals mu sub I standard states plus RT ln. The vapor, this P sub I asterisk is the vapor pressure of the pure substance over the standard pressure of 1 bar. So now what we're going to do is that equation we just had on the previous slide, going to take that and subtract this equation from it. So on the left-hand side of the equal sign, we get mu sub I minus mu sub I star. On the right-hand side, we get this minus this. This is from here. Now, a bunch of stuff cancels here. The mu sub I standard states cancel. Pull out the RT, the P standard states, that cancels, and we get this equation right here. Rearranging this a little bit by bringing over the mu sub I star to the right-hand side, we get this equation here. This says that the chemical potential of component I in a solution is equal to the chemical potential of that component when it's pure plus RT ln of the partial pressure of that component over the partial pressure when it is pure. But for an ideal solution, which is what we're talking about at the moment, we know elsewhere the partial pressure is equal to the mole fraction times the partial pressure of the pure substance. Rearranging this a little bit, solving for the mole fraction, we can replace this with the mole fraction. We get this equation right here. And this looks exactly like we got for a gas, for an ideal gas, back in chapter 6. Because the chemical potential is equal to delta G of formation of that substance, we can apply the same analysis we did back in section 6.5 for a mixture of gases to the solution, a mixture of liquids. Mixture of solutions, a solution. The results are this. This is exactly what we got back in section 6.5. Now here, let's look at these two. So these, we saw these before. For an ideal solution, the change in volume of mixing will be 0. Because remember, in an ideal solution, the strength of the interactions between the solvent, and solute particles are all identical. So it's not we won't change the volume, and likewise, the delta H will be 0. So a little example here, we have this many moles of benzene, this many moles of toluene, mix them, form an ideal solution, and we just want to calculate delta G of mixing and delta S of mixing at 298 Kelvin and 1 bar pressure. So we have our equation for delta G of mixing. We're going to need the mole fraction of each component. So the mole fraction is just in moles of that component divided by the total moles. So adding up the moles of both components, we get this. Taking the moles of benzene, dividing by the total moles, we get the mole fraction of benzene. Likewise for toluene. So now plugging into our delta G mixing equation, check my math, but I believe we get negative 12.15 kilojoules. Likewise for delta S in mixing, negative NR, sum over I of chi sub I ln chi sub I. Plugging those numbers in, we get negative 40.794 joules per Kelvin. So what that tells us, because delta G is negative, that it's a spontaneous process, and that makes sense. Mixing is always going to be a spontaneous process for an ideal solution, and the entropy decreases, excuse me.